If you work with big data, you've hit the same wall. We all have memory. How do you count the most frequent items in a massive, never-ending flood of data without saving everything? What if I told you there's a way to count the most popular things by mostly not counting? Imagine a relentless stream of data. We're talking millions of clicks, network packets, or search queries every single second. It's like trying to drink from a hills. In this flood of information, our job is to figure out which items are the most popular, the heavy hitters. Think of it as finding the most watched video on a platform in real time. The obvious way to do this would be to use a giant hash map with a key for every unique item and a value for its count. But with billions of unique items, that hash map would be gigantic. It would take up way more memory than we can afford, and it would be incredibly slow. We simply can't store everything. This is where the genius of the Misra-Gries algorithm comes in. It's a solution that's so simple, it feels like a magic trick. Instead of trying to count every single item, we decide up front that we're only going to use a small, fixed number of counters. Let's call this number K. Think of K as the number of slots you have to track things. This is our trap. We're not tracking every single item, only the potential frequent ones that are lucky enough to grab one of our limited spots. This small set of counters is our entire memory. It's tiny compared to the data stream, but it's all we need. So how does it work in practice? The algorithm has two main rules. The first one is the easy part, the increment rule. We first check if this item is already in our small list of K counters. If it is, great. That means it's a potential heavy hitter. We simply find its counter and increase its count by 1. This is just like a normal counter, confirming that this item continues to be popular. For example, if Apple is already in our list with a count of 50, and another Apple comes in, we just update its count to 51. Simple, right? This part makes perfect sense. We're rewarding items that we've already identified as potentially important. Now for the second rule. This is where the real magic happens. This is the core trick of the entire algorithm. What happens if a new item comes in and it's not in our list of K counters? We have two scenarios. If our list isn't full yet, meaning we have fewer than K items, we just add this new item to the list with a count of 1. But what if our list of K counters is already full? This is the key moment. We don't just ignore the new item. Instead, we do something radical. We go through every single one of our K counters, and we decrement their counts by 1. all of them. After we do this, any counter that hits 0 is now free. We can then take our new item and place it in one of these newly emptied slots with a count of 1. This is the purge. Only items that appear very, very frequently can survive this constant subtraction. Infrequent items will have their counters quickly drop to 0 and get kicked out. So, why does this bizarre trick of subtracting from everyone actually work? It works because of what I call proof by subtraction. When we decrement all K counters, we're essentially creating a battle for survival. Think about it. For an item to keep its count high and stay in our list, it has to appear frequently enough to overcome this constant tax or decrementing process. An item that appears only once in a while will get its counter decreased over and over by other incoming items, and it will eventually hit 0 and be forgotten. But a true heavy hitter, an item that appears thousands of times, will get incremented so often that the occasional decrements won't be enough to kick it out. The count will keep growing. This decrement step is the filter. It cancels out the noise and lets only the truly frequent items, the strong signals, survive. Of course, there's a trade-off. The cost of this incredible efficiency is that the result is an approximation.